All right, so now we're going to describe the pseudocode for adaptive quadrature. And so before I do that, let me say something a little bit about the way that data is stored. Okay, so I'm going to start with u is equal to a, w is equal to b, right? So that's sort of the initial interval, and then the data is stored in a vector as follows. So I store the left side, the step h, okay, f at u plus h, and f at u plus 2h. So I think of the interval from u to w as being 2 times h, all right? And then I have s, which is containing the Simpson's approximation of the integral over that interval from u to w. Okay, so 2h is equal to w minus u. Okay, and then s is equal to s of uw, right, which is h over 3 f of u plus 4f u plus h plus f at u plus 2h. Okay, all right. And it's h over 3 because the entire interval is length 2h, right? It's not h, okay? All right, so then we have a condition. If you recall, there was this computable approximation to the error, which was 1 over 15 s of uv plus s of vw minus s of uw, all right? And you wanted that error to be bounded from above by epsilon times the interval length, which is 2h over b minus a. So the appropriately sort of equipartitioned error, it's like where the partitioning is by the length of the interval relative to the total length of the interval. All right, so I can multiply this throughout by 15. So this means that s of uv plus s of vw minus s of uw is less than equal to epsilon 30h over b minus a. So that's the condition, all right? And then in absolute value, if you will. Okay, and this thing I'm going to call S1. This is going to be S2. And this is what I'm going to call S. So you have an interval for u, v, w, right? The Simpson's approximation over the entire thing is S, over the first subinterval is S1, and over the second subinterval is S2. Okay, all right. So if the sort of inequality holds, it's like then you keep it, and if not, then you do a subdivision. Okay. So if the inequality doesn't hold, it's like then you replace this vector, it's like with 2 additional vectors which contain the information for each of the subintervals. So that's sort of the basic idea behind what's going on. All right, so let's maybe start talking about the algorithm now. So the input is the function f, right? The initial interval a to b, the sort of the tolerance epsilon and n, okay, and n is more or less sort of an upper bound to how large it's like how many subdivisions you want to do. Okay, so this is sort of sort of an upper bound to the number of subdivisions you have, even if the error condition is not satisfied. Okay, so it's always important to have that because sometimes the error condition can't be satisfied because maybe f is not regular enough, All right, and so in that situation, you want to make sure that the algorithm is guaranteed to terminate, and that is going to select the max level, and that guarantees it terminates. Okay, so delta is going to be b minus a, sigma is going to be 0, h is going to be delta over 2. All right, then c is going to be a plus b over 2. And then k is going to be 1. fa is going to be f at a. fb is going to be f at b. fc is going to be f at c. So c is the midpoint and a and b are the endpoints. Then s is going to be fa plus 4 times fc plus fb, the whole thing divided by, or the whole thing multiplied by h divided by 3. Okay, and then v1 is sort of the initial vector which contains this data. So v1 is ah, so the left interval, the length of the thing, the function values fa, fb, or fas, fc, and fb, and then the computed Simpson's approximation over that interval. Okay, and then while k is between 1, between or equal to 1 and n, you do the following. So there's an upper bound how many iterations again you take. So h is equal to v2k, right? So 2 here denotes the second component, which is the step. So you just take the step and you divide it by 2, right? fy is equal to v1k plus h. So you evaluate it at a new point, okay, and then s1 is equal to v3k, the third component, okay, plus 4 times fy plus v4k. So I'm reusing the function evaluations. I'm storing the function evaluations in that vector so that I don't have to repeat that. So that saves a little bit of computational power, right? So again, this is, so you're coming into this, it's like having computed, it's like the Simpson's approximation to this interval. This is computing the Simpson's approximation over 2 equal subintervals. All right, okay, then fy is that new point. So how should I say it, right? This is u, this is w, this is v, this is y, and that point here is z, right? Okay, so hopefully you get the idea. Okay, so fz is equal to f evaluated at v1k plus 3 times h, and s2 is equal to v4k plus 4 fz plus v5k. All right, whole thing multiplied by h over 3. So again, you're reusing, it's like the function evaluations, which is stored in that vector. Okay, and then you have to check the error condition, right? So this is the error condition, all right? This thing is the error condition, right? So if the absolute value of s1 plus s2 minus s, okay, s is stored from before, so that's v6k, is less than 30 times h divided by delta, then sigma is equal to sigma plus s1 plus s2, okay, plus s1 plus s2 minus v6k over 15. All right, so basically what this is saying is that if the error condition is satisfied, then I add the computed approximation to the integral, right, to my accumulation for what that sum is. Otherwise, I keep going. Sorry. Then if k equals to 0, then output sigma, and I stop. Okay, then else if k equals to n, output failure, and I stop. Okay. All right. Okay. So not quite done yet. Right. So okay. So if this condition is not satisfied, then I can update. I will replace sort of that vector as like corresponding to storing this data with two new vectors, right? Okay, then fw is equal to v5k, right? And then vk is equal to v1k, h, v3k, fy, v4k, and s1. All right, so this sort of updates with a new vector, and then k equals to k plus 1, and then vk is equal to v1 k minus 1 plus 2h, okay, h v5 k minus 1, fz fw, and s2. Right, so the point is that, yeah, so you're adding in this sort of new data to it, okay? And the reason why I had to store this was because I was updating vk with this data, so I had to store this function value in fw. That's why this is different from that. Okay, and then there's an end if, and then end do, end while. Okay, so the basic idea is quite simple. First you initialize, it's like for the initial Simpsons values, you set up first with just one interval, right? And then you take that interval, you subdivide it, you compute Simpsons, it's like on each of the pieces separately, and you use the difference s1 plus s2 minus s to get an estimator, which then you check, right? So you check whether this sort of accuracy condition holds, and if it doesn't hold, then if it does hold, it's like then I increment, it's like, and I move on. Otherwise, I do this sort of subdivision process. Okay. So you could also envision doing this recursively, but this is sort of one way to do it. And again, it's like the basic idea is that either you check the condition and either it's satisfied, and if it's not satisfied, then you do sort of this, you replace that interval with two equal subintervals, and then you sort of keep going. Okay, so that's the basic idea behind this. All right. Yeah, so that gives you an algorithm. It's like which will then either A, it's like, you know, output the, you know, it's like the sort of adapted estimator, which modulo this assumption we had that the fourth derivative is almost constant along sort of that interval, gives you a very, very good control. It's like over the error, it's like you have by replacing the exact integral with this numerical quadrature approximation. Okay, so let me just stop here.